Okay, good morning everyone. My name is Eric Gant, and I am a technical support engineer here at Pointwise, and I'm going to be giving you your webinar presentation today titled Meshing Forensics 2, Overcoming Common Structured Gridding Pitfalls. I know in our material that we've sent out and on our website that we had listed that Carolyn Deere would be joining me today. Unfortunately, due to other events, Carolyn is not going to be with us today, so it's just going to be me doing the presentation and following up with your questions at the end of the webinar. And having said that, please do hold your questions until we finish up, and at that time you can use the field or the window that's in your webinar application that is there for you, labeled questions, to type in your question, and I will answer them as they come up at the end of the webinar. So today we want to touch on some topics that our users frequently run into when they're working primarily on structured meshing projects. So we're going to talk about some things including assembling domains, blocks, some distribution things that come up with users trying to distribute their connectors, what to do when you need to get a structured domain onto your underlying database geometry, and then a little bit about diagnostics at the end of the webinar. So jumping right in with this model that you see on the screen that I have displayed right now in Pointwise, and by the way, I am using our current production release of Pointwise version 17.1 R3. It's available on our website. I have a fairly simple topology here that is the starting point basically of a structured grid on the interior of this 747 nacelle geometry that's going to have eventually, if it were completed, a butterfly style topology on the interior of these blocks. But I've just kind of set up a little bit of the topology here to just go through a couple of very common situations that our users run into. The first thing that I want to do is try to assemble a domain from these connectors that I have here at the back end of the interior of the nacelle. I'm going to change my mask so that I'm only selecting connectors. I'm going to size a selection box about these connectors at the back end while holding the Shift key so that I select only those entities entirely within the box. And then I'm going to just click on Assemble Domains up here on the toolbar. Now in my Messages window, it tells me immediately that 0 domains were created, and there are 5 connectors that I had selected that it didn't use. This particular case is, of course, the most common example of why you cannot create a structured domain, and that is because the dimensions of my connectors are not appropriate for it to be able to create a computationally rectangular region, which is required for a structured domain. If I simply take my mouse and mouse over or hover over these connectors in sequence, I can immediately look down at the bottom of the interface, the portion of the interface that we refer to as the status bar, and you can see down here in this region it will give the connector name and its dimensions. So this is con-3, its dimension is 21. Up here at the top I have con-4, also dimension 21. Likewise at the bottom. And then these 2 connectors that would form kind of the front end of this domain, they also each have 21 grid points. I can also see this information if I expand the connectors portion of my list here on the left-hand side of the interface. Whenever I mouse over one of these entities, it's also highlighted in bold in the list, and I can see the dimension of the connectors there. This is a pretty easy way right at the top of the interface to see what my dimensions are and to tell fairly quickly, in this particular case, in most cases, where my discrepancy is in my connector dimensions. Now, the next step obviously is to change the dimensions somewhere so that I can put these connectors together into the domain that I need. My choices are to either redimension these connectors at the front, which are already used in the purple domains that you see, or to simply change the dimension of the connector at the back end, which would be the simplest solution. There are two ways, or two commands primarily, that you can use to do this. You can change the dimension right at the top of the interface by simply selecting the connector. I'll select this connector at the aft end, con-3. You can see now it's highlighted in white. It's also highlighted in the list with a blue background color. And then I can just come straight up here to the grid toolbar, click in the dimension field, and type in a new value. This particular connector needs to have a dimension of 41. Type in enter. Its dimension is updated immediately. It also provides us a info message down here in the messages window indicating that it has been dimensioned. The other way that we can go about changing the dimensions of our connectors when we need to is to actually go to the grid menu and use the dimension command panel. The command panel is set up to give us a lot of additional capabilities, and we're not going to be able to cover all the functionality that we have in this panel today. But specifically, I want to point out that when you use this command panel, it will try to maintain your topology and your computationally rectangular domains for you automatically, and will propagate dimensions for you based on the nature of the domains. So for instance, if I come in here and highlight one of these connectors that are already used in these domains at the front of the topology, you see that all three of these connectors on the sides of these two domains highlight immediately at once. That's because Pointwise knows that all of those connectors must have the same dimension based on the topology. If I go in and click on this connector and change its dimension, all three of the connectors will have the dimensions changed automatically. This is one way that Pointwise maintains your topology and also actually accelerates the work of trying to change the dimension in the structured grid later on in your process when you may need to. I've already got the dimension set how I need it to, so I'm not really going to go through and make any more changes using the dimension panel. I'm going to go ahead and use my selection box again after I rotate the model just a little bit, holding the Shift key and selecting these connectors again. Click on Assemble Domains on the toolbar, and Pointwise creates successfully the domain that we wanted to create. And down here in the messages window we see one domain created and there were no connectors unused. Our next step is to create some domains up here at the front end of our topology. When we assemble these pieces together, we would expect to get three domains here, two that wrap around in a O-type fashion around the central domain. I should probably go ahead and check dimensions here just to make sure I have consistency, because I did use a default connector dimension of 21. As you can see in the list, all these connectors essentially have the same dimension except for the one that we've just changed. The dimension of this connector around the arc of the cell is, of course, 21. It needs to match these two connectors that we have here on the interior. One of these is 21, the other is 11. So we need to make an adjustment here. Basically, I'm going to go ahead and change the dimension of both of these connectors, whose dimensions are 21, by selecting them, and again, just simply using the dimension widget right here on the grid toolbar, type in a value of 11, hit enter, and so now this connector, the one adjacent to it, will have the dimensions necessary to match the opposing connector for that domain. I'll rotate the model around again just a little bit. I'll use an inbox selection, again, to select all these connectors, and go ahead and tell Pointwise to assemble domains. Well, I see now, after this process, I have two new domains created and I have a couple of connectors that have gone unused. So I have another situation here where I've tried to create a structured domain and it hasn't successfully assembled using the automated command. I'm going to unselect all those connectors by clicking in the display. Once again, I'll once more verify my dimensions, 21 here, 21 here, 21 on the nacelle edge, and we have two connectors, dimension 11. So all the dimensions should match up properly to form this domain. There must be some other issue. And this brings us to the second most common issue or pitfall that users can run into when trying to assemble their domains. And this is one actually that applies not only to structured meshing, but of course unstructured grids as well. The other issue that comes up is sometimes you'll have a situation where the endpoints of your connectors, which are referred to as nodes, do not match within the default node tolerance. The default node tolerance is found in the File Properties panel. If we look over here, we'll see a node tolerance of 0001, and that's what we have set up for all new sessions of Pointwise, and it works quite well under most circumstances. So that means that all of the nodes in this set of connectors must lie close enough to each other to a value that's less than that tolerance in order for Pointwise to assemble these loops of connectors into domains. The easiest way to check for a possible issue with the node tolerance or nodes not matching is to simply go to the grid menu again and pull down to the merge panel. In the merge panel we see a number of options. My favorite, of course, for checking for the node tolerances is to check on merge pairs of entities, because in this frame we can check connector pairs, we can check node pairs, and we can actually also check node connector pairs, which allows us to find situations where we could merge the interior of a connector with a node. Right now we're looking for possible issues where our nodes are not matching within tolerance. This is a selective command. It's not automatic. It allows you to choose what you want to merge. So you can type in a relatively large value of the tolerance in this field. I'm going to type in a value of 0.1, which of course is 3 orders of magnitude greater than the default. As soon as I hit enter, Pointwise looks through the entire topology in the mesh that I have right now and puts up any candidate pairs of nodes that may match within this new tolerance value, and it lists the actual delta between the nodes here in the table. When I mouse over this entry in the table, the pair of nodes, you can see it gives me the connector names and the end, of course, of the connector or the node. It also highlights that node pair in the display window, and I can see it's up at the top lip of the inlet of the nacelle. I can also mouse over the nodes in the display window and have them again highlighted in the table. There's only this one set, and this is clearly going to be the issue that we're having assembling our domain that we're trying to get. All I need to do is select it in the list or in the display. It's highlighted in white just like any other selection, and in blue in the list. If I had multiple merging operations, I could click on Apply to have those merged and go on to the next. But this is the only one I need to do. I can just click on OK to have the merging done and exit the panel. Now we can go ahead and select these connectors again. I'm going to rotate my model back around to make selection a little easier with the box. Select the connectors that I need to use, click on Assemble Domains again, and my domain is created successfully. So just to recap this first piece of our webinar here, the two primary things that users run into when creating domains or assembling their domains is, first of all, for structured grids, having the dimensions correct. Of course, that's the most common thing that comes up, is that users just need to adjust a few dimensions here and there in order to form the topology together into a computationally rectangular region. And then, of course, the second most common pitfall that you may run into are nodes that mismatch, as we saw in this example. So those are the only examples that I wanted to show for this particular project case that I have in right now. I'm going to read in another file so we can look at some more topics. I do not want to save these changes that I've made to this case, and I'm going to replace it. This example that I've written next is a favorite of mine that shows a number of different types of little pitfalls, I would say, things that you can run into when assembling topology that really aren't very common in most meshes, but they can come up from time to time, especially when you start working on complex geometries, because invariably you're going to come up with more complex topology because of that, and you may run into some of these things. What I have here is a pretty simple geometry, but it is one that I've seen in a number of cases that I've worked on personally in the past and that some of our users have also encountered. This is sort of basically like a strake region for some type of a missile or an aircraft geometry, and the strake has thickness upstream and comes down to a very sharp edge at this trailing edge that you see here where I have this connector highlighted. And I've generated a topology here, essentially an O-type topology, that I wish to have wrap all the way around this strake type geometry. Pretty much all the topology is here in terms of the connectors, and I have a few domains that are already created that we need to generate a block around this geometry. So what I would like to do, of course, when I've done all this work, is to just simply try to assemble the block automatically with the assemble command. I need to make sure that my mask is set so that I'm selecting both the domains that I already have and the available connectors. And then I'm just going to go ahead and again use a selection box about all the topology and click on, this time, Assemble Blocks. The Assemble Blocks command goes off and tries to assemble as many domains as it possibly can from the existing topology, and then it also will go ahead and try to assemble all of those domains into blocks where possible. What we see is that this command has created 8 domains, but there are a number of connectors that have been unused, and I can see immediately that I have some areas here where I do not have domains that have been created that I need to form a block. First of all, if you look at the straight geometry itself, I can see I have a domain at the bottom, but I do not have a domain on the top surface. Secondly, there should be a domain closest to us that wraps all the way around the trailing edge of the strake. That domain is also missing. So we need to figure out why and what we need to do to overcome these missing domains. These are a couple of situations that, unfortunately, the automated assemble command will not be able to take care of for us because of other circumstances. Let's look at the upper surface of the strake first. What's happened here in this situation is that we have a domain that the assemble command created on the bottom. For it to be able to create a domain on the top of this geometry, it'll actually have 2 edges in common that it shares exactly with the other domain that's already existing. In general, pointwise tries to prevent you from creating duplicate topology. And any time it comes up on a situation where there are at least 2 common edges, entire edges of a domain, it's not going to create this other domain automatically. And we're actually going to have to use the command that we have available to do this in a more manual fashion called Assemble Special. I'll go to the Create menu, Assemble Special, Domain. This command allows us to essentially define the individual edges by connectors and move from one edge to the next in sequence, and then save the domain when we have it completed. And actually, there's a feature here in the panel called autocomplete that's turned on by default to that will try to complete the domain for us, if possible, based on the topology that we've already created. I'm going to start at the root here and select this connector. It shows 41 grid points on that particular edge. I'll click on the next edge button. I'll select the connector at the trailing edge. Again, the next edge button. It automatically selects this third connector here for us on the outboard edge of the geometry. It did that based on the dimension that it knows it needs because of the first edge. Now all we need to do is begin defining the fourth edge of this domain. I'll select this first connector. As soon as I do that, a dialog has popped up. It says domain will overlap the following, domain-9, which is the domain on the lower side of the strike. So these are the circumstances that I was referring to just a minute ago. These two domains will share at least two edges entirely, and there is a possibility of producing a duplicate domain, and that's why we get this dialog, and that's why the assemble command, the automated assemble command, was not able to generate this domain automatically. We do want to continue. We'd like to keep this domain, so I'll click yes, and we have our domain on the upper surface of the strike. The next thing that we want to look at is this domain. It's kind of at the outflow of our topology here at the trailing edge of the strike. This domain, in order to create it, requires that this connector at the trailing edge be used twice in order to define the topology correctly. That's why the automated assemble command was unable to create this particular domain. So it's another somewhat special situation, again, that doesn't come up that frequently, but can in various topologies. Again, we'll just go ahead and use Assemble Special to assemble this domain. I've selected this first connector up here at the upper top of the strike. You can see there's an arrow that's drawn on here by default indicating a direction for the loop of connectors. That arrow is not important. It's not telling you that you have to go in that direction. It just has to assume a direction because I've only got one connector selected. I can just as easily come down here and select this connector on the trailing edge of the strike. I need to remove that last connector since I did not say next edge because this does need to be a new edge. I have a command available for that. Remove the last connector. Go ahead and click on next edge. Now I can select the connector on the strike trailing edge. I need to select it again because the domain actually traverses back. And you can see I have an arrow pointing in both directions now for this particular connector, indicating that it has been used twice. I'll click on next edge. As soon as I click next edge for the third edge, it automatically determines the rest of the topology, finishes and initializes the domain for me. So now it looks like we're in good shape. We have all of the domains that we need to surround this particular volume and form a block. I'm going to zoom back out just a little bit. I'm going to click on OK to exit from Assemble Special for domains. I have my mask still set for selection of domains and connectors, so I'm going to again just size a box around all the topology and click on Assemble Blocks. Well, unfortunately, we have 0 blocks created from the automated assemble command, and all of our domains are unused. So there must be some other issue in the topology that we need to figure out. So what we need to do is now go back to the merge command and use that as a tool to try and figure out whether or not we have what we refer to as coincident connectors in our topology. In other words, a situation where there are two connectors in the same physical location that are not obvious but are being used by adjacent domains separately, such that one domain uses one of the connectors, the adjacent domain uses the other. In order to form domains into faces and into a block, all the domains in the face and faces must share connectors between them in order for everything to be linked properly. Let's go to the grid merge command. I'm still on node-node merging. I'm going to click over to connector-connector merging. And you'll notice using the same tolerance I used before with nodes, Pointwise immediately puts up a set of connectors. And when I mouse over, I can see at the very bottom of the topology there's a pair of connectors that are being highlighted that were not obvious, but there was two connectors there. So what we need to do is merge these two connectors together, and then we'll have a tight topology that we can use to form this block. I'll select the connectors. I'll click on OK to have them merged and to exit from that panel. So now it appears that we've taken care of the duplicate connector issue or coincident connectors. I'm going to try one more time to assemble this topology. And I wasn't able to assemble it. And the reason is we still have a special case scenario here in this block. And that's the topology, again, that's around this strake. Because of the way we need to form a face on the strake using the upper and lower domains, and the fact that they share two different edges and two different connectors, it's difficult for the automated disassemble command to form that topology automatically. So just like we did for a couple of those domains, we're going to use the symbol special block to overcome what's stopping us here. In this panel, we just simply have to define each individual face and save the face as we go. Structured block has to have exactly 6 faces, which means a structured block, in order to be created, would have to have at least 6 domains. We obviously have way more than that, and we have plenty to form the topology that we need. I'm just going to go ahead and do this symmetry domain at the top. I'm going to use Control F on my keyboard as an accelerator for save face. I'll select the domain down on the bottom symmetry, Control F again. And one thing that's interesting to note when you use this command is that once a domain has been used, it's assumed that we're only going to use it once in the formation of the faces for this block, and so it cannot be selected again, which is a real convenient feature for this assembly process. I'm going to go ahead and select this domain that's at the outer boundary. That's an entire face. I can save that one. And I'm going to go ahead and select this domain that's at the outflow area at the trailing edge of the strake and save that as a face. And let's do the one that's at the inflow or at the leading end of the strake. So I've selected this domain down at the bottom. Now this face obviously requires all of these domains that I have at the front end. And so we have to select all of these domains before we try to save this as a face. This is another example that I like to show when users are trying to assemble a complex face of multiple domains that you may run into now and again when you're assembling a complex face. I have all these separate domains that I'm putting together, and as I've chosen these, I've formed an area in my face where there's going to be an open region. Instead of having selected this domain next, I selected this outer domain, or the one that touches the symmetry plane. This domain attaches to the face in 2 physically separate locations. And so these are 2 separate possible locations where the new domain can be linked to the existing face. You'll see over here in the diagram I have a bold pink outline for this upper connector, and there's a list. And I can click on link 1 and link 0 and have them both highlighted in the diagram and in the display window. This is a perfect example of a case where the linkage that I choose doesn't really matter. And that's because all of these domains are going to be put together eventually, and it will all be closed. There is no one or the other choice that is correct. They are both valid. And so in this example, I can choose either, tell Pointwise to use the selected link, and then as soon as I select the remaining domain, the face is completed and everything is linked together internally. There are no issues with the face. I'll save this face. That leaves us now with one remaining face, and that'll be the one that wraps all the way around the straight geometry. Two domains. So let's select those. This is another example of where Pointwise wants us to make a linkage selection. And in this example, it's very important which one we choose. The topology for this block is wrapping around the outside of the strake. So we want the face on the strake to also wrap around the outside edge of the strake. That means we want these two domains actually to be linked along this outer edge, such that if this block were to be unfolded computationally, this seam here at the trailing edge would peel apart. So we do not want to use the linkage that's currently highlighted, link 0. We want to click on link 1 and use that linkage instead. So again, this is an example of a face where the linkage does matter, and you need to be able to visualize how the block fits together computationally in order to pick the right linkage. Use the selected link, save this face. Pointwise is happy with the block definition and has gone ahead and put up a default set of coordinate directions, computational coordinates, which can of course be changed later in the meshing process if you need to, if this is not the coordinates that you want to have for your solver. And you can do that using the edit orient command. Everything looks good here, so we can just click on OK and save that block. So we went through a number of steps there in order to get to this final end goal of creating this block topology. But as I mentioned, this topology is a good example case that illustrates a number of things that you can run up against in a more complicated topology. And they're not bugs or problems or even issues with your grid when you run into them. They're just special case scenarios that require a different command in order to put the topology together properly. Okay, that's all I need to show for this particular project file. Let's move on to our next example. I'm going to be reading in a database file by itself without any mesh. So before I do that, I need to go ahead and clear Pointwise out, so we're starting with a clean slate. To do that, I'm going to go to the File menu and click on New. I do not want to save my changes that I've made to this example. I'll click on OK. And so Pointwise essentially resets the interface, and we're ready to start a new project. I'll go to the File menu again. Import Database. I have this same nacelle geometry that we were working on earlier. I'm going to read that in. We have some options here that we can set for visibility controls and also for solid modeling. I'm not going to mess with any of these from the defaults. I'm just going to click on OK and read in the geometry. So the example that I'm going to get to here for this particular case is to demonstrate a few things. One has to do with connector dimensions, and specifically actually with connector distribution. And then after we look at that, we're going to move on to a surface grid that spans multiple database surfaces and the tools that we have to make it conform or take the shape of the database. Before I begin, I want to go to my Layers tab and turn off some of this geometry. I really only want to look at the outer nacelle geometry for this example. I don't have any labels here, so I'm just going to have to, by trial and error, see what's in each layer. I click that one off. That's actually the inner nacelle. That's good. Layer 38 has my outer nacelle. I'm going to go ahead and double-click the description for that and rename it. And so this must be the hub, layer 53. I'm going to turn that off as well. I'm also going to come over and for defaults, I'm going to set a default connector dimension of 41 so that all new connectors that I create will have that number of grid points assigned automatically. And then what we'll do is go ahead and create some connectors, and I'm not actually going to use one of our parametrically defined connector tools. I'm just going to create straight line segment connectors using the corner points of these surfaces. So I've just moused over and selected the back corner of this upper surface, and you'll notice whenever you're at a pickable point in the geometry, you do get a bullseye type cursor. I'll click at the front end of that surface, and then again up here at the lip of the nacelle. I'm going to click on apply to save that as a new connector, and then allow me to create another connector. And of course, these are highly segmented or faceted shaped connectors because they're linear between control points. And then one last connector here at the inlet lip of this nacelle. And then OK, this time to save the connector and go ahead and exit the panel. So the first part of this example is just to kind of show that there are, of course, many ways in Pointwise to create your connector topology. And sometimes the geometry can be fairly complex in terms of the surfaces that it's made up of, and it may in some cases actually be quicker and easier to create some simple segmented connectors like I have here across a complex geometry, and then just project them onto the geometry in order to get the topology I need. The reason this comes up actually more often in structured grids than unstructured is because it's more often the case that a structured topology is not going to follow the underlying geometry. Whereas for unstructured meshes, very often we can allow the topology to follow the geometry, or it's just very simple to combine unstructured surface grids together if we need to without regard to any topological restrictions. Before I go ahead and project these connectors to get them onto the database, I'm going to make one more change, and that is to do a little bit of connector clustering on these lengthwise connectors on the nacelle. So I've changed my mask here that allows me to select spacing constraints. I'm going to select these two at the aft end. I'm going to come up here into the grid toolbar and type in just a value of 1.0. And then again, up here, the inlet area, up here I'm going to use a value of 0.5. And just to visualize what we've done here, we can of course select the connectors and turn on their grid point display, and we can see that I have distributed these connectors on the edges of the nacelle to the front and the back ends. The other two connectors are equally distributed. Alright, I already have the connectors selected. Let's go ahead and place them onto the geometry using the Edit Project command. It opens a new panel. It tells us how many of our points are currently on the geometry. There's only 9. The points at the corners or at the ends. It's set up to use the default projection type, which is closest point. Works really well in the vast majority of cases. So let's just go ahead and click on Project. We can now see in yellow the projected shape of the connectors versus the original shape of the connectors in their white selection color. It looks like the changes are going to be pretty good. Let's go ahead and click on OK to save the projected connectors. And then let's go ahead and immediately assemble them into a new structured domain. So far, so good. Everything looks pretty good. I'll go ahead and point out this domain has been rendered in green. This is a question that comes up frequently from our users, particularly newer users to Pointwise, and that is, why are some of my domains green and some of them purple? Travis Kerrigan actually touched on this in our last webinar, but it's a point worth mentioning again. When a domain is initialized the first time when the domain is created, there are several methods that Pointwise uses to try to initialize the interior points. Primarily, it's either going to use what we call a standard TFI, or transfinite interpolation, and those domains are rendered in green, as we see for this case here. The other is a parametric TFI. Parametric TFIs require that all of the bounding connectors lie on the edges or interior of a single database surface. When they do, that particular domain will be initialized in the parametric space of that underlying surface, meaning that it automatically has the shape of that database entity. Those domains initially are always rendered in purple. However, changes can be made to any of these types of domains after the fact that may change the nature of whether or not they actually have the shape of the database. And so you can't always rely on the color later on. One of the first things that we notice in our example case here, and I'm actually going to go ahead and select these connectors again and turn off these points. We'll select them in the list. And we're going to go points off, so that now all we're really looking at is the distribution of the interior of the domain. And we can see up here at the leading edge, or the lip of this cell, we have a little bit of a clustering issue here that we don't really want. In our grid, we'd really rather have a smooth distribution of points all the way up and clustered to the lip like we had originally in the connector. Our first thought here is to go in and adjust the spacing constraint just like we did originally when we created the connector. So I'll switch my mask so that I'm selecting spacing constraints. I'll select this constraint here at the lip, and maybe I want to increase it a little bit to see if I can pull those points up the way I expect them or want them to be. Let's change it to 0.1, for instance. Well, I did see a little bit of a difference or change in the distribution, but it's really not giving me the smooth distribution that I expect. Let's change it back to 0.5. And I can see that it has adjusted it again, but it's still not a particularly smooth distribution. Well, there is a good answer or reason for this and why this is taking place. Whenever you project connectors onto the database surfaces, all of the grid points of the original connector are projected onto the database. When that happens, those original grid points actually become control points that define the shape of that connector. And we can see that by selecting one of these connectors and going to the Edit Curve command. All the original grid point locations are now control points defining the shape of the connector, and that's true for each of the segments in the connector. In addition to the points becoming control points defining the shape, they are also locked into what we call a type general distribution. In other words, the distribution of the grid points is being stored discretely and is not actually a result of a mathematical function. And we can see that if we go to the Grid Distribute command panel. We can click on the Functions tab, and in the function list we see an entry called General. It's grayed out, but the button is selected, indicating that this connector has a type general distribution. So Pointwise is trying to maintain the distribution of these points discretely. So when I change those spacing constraints, it is doing some local adjustment of the distribution, but in general most of the points are relatively fixed. And you can see this in cases when you try to start adjusting distributions by spacing constraints and your distributions are not really changing fluidly the way you would like them to. The solution is just to simply come into this panel and go ahead and change these connectors to a hyperbolic tangent, or what we refer to as a tanh distribution. This is the default distribution function that we have that's used for all new connectors in the code. And then we can just click on Apply or OK to exit the panel. So what we really want to do is come back in with all of these connectors and change the distribution function for all of them. So I'll just click on OK to change this one, and then I'll select the others. We'll go back in, function. We have a mixed set here. One of these did not get updated. No, it's just a remnant from the previous session. So we want them to be hyperbolic tangent. Click on OK. And so now all the points on all these connectors are free to move on the connectors via that mathematical function, the hyperbolic tangent. We also need to go back in and update these spacing constraints because they've been changed automatically because of the general distribution that was on the connectors before. So we can do that again by just changing our mask, selecting the spacing constraints. I used 0.5 up here at the inlet before. It's still in my text field. I just need to click in there and hit enter. And then I'll select the 2 at the aft end and reset those to 1. So everything looks good here in this domain now. The next thing that we want to talk about pretty quickly is how do we get this domain to take the shape of the database entities underneath? If I rotate the model around and kind of look at the nacelle from the bottom, I can see my domain is just a flat, straight shell and does not really take the shape of the nacelle itself. There are 2 ways to go about doing this. We can select the domain, and just like we did for the connectors, we can use Edit, Project to place the domain onto the underlying database surfaces. The table tells us how many points are on, how many are off. The points that are currently on are going to be those points that are, of course, on the connectors around the perimeter. We can go ahead and click on Project. Just like for the connectors, we see in yellow the new shape of the domain versus in white the selected color of the original domain. If we're happy with the results, we can just go ahead and click on OK. That saves the new projected domain, and it now has the underlying database shape. We can verify that using the Examine Database Associativity diagnostic, which renders all the points that are on in green and those points that are off in red. We have 2 points here that fell where we have branch segments in our connectors between database surfaces, and so those are not marked as being on the database or database constrained, although they essentially occupy the same physical space. This looks good. The other way that we can actually force a domain to lie on the underlying database surfaces is to use the solve command. We go to the grid menu, pull down to solve. That puts us into the solve panel where we can run the elliptic PDE solver that we have in Pointwise, which allows us to improve the quality of structured domains by producing more favorable orthogonality around the boundaries and in the interior, and of course overall smoothness. While the solver is running, we can have it maintain the shape of the domain on the underlying database. Since I already projected this domain onto the database entities, this command automatically defaults to shape database, and it has already picked up the 4 domain or the 4 database surfaces that are necessary to use to maintain its shape. If I cancel out of this and undo the projection of the domain, and then take the domain into the grid solve command, I'll see a little bit different default setup. Since the domain is free, it defaults to free as its shape in the solver. But I can change that using this pull-down list right here, switch it to database, and as soon as I do, it looks at all the perimeter connectors to see if there's any associated database surfaces it can use as defaults. And of course, it does pick up the same 4 surfaces based on the connector associativity. We can immediately go in to the Solve tab of the solver, type in a number of iterations, say 25, and click on Run, and go ahead and smooth the domain while maintaining it on the underlying database surface. Everything looks good. We can click on OK, and we're finished with the domain. Again, we could look at this in the examine command using the database associativity diagnostic to see that it is indeed on the database surface. I have one more quick topic for us to talk about, which revolves around diagnostics. Let's read in another file. This particular case is our axial turbine grid that is one of our tutorials for Pointwise, and this is the structured version of the grid. And one of the things that comes up from users frequently is, first of all, maybe they've finished this grid and run it into their solver and gotten some feedback that the solver is either not converging in a particular region of the grid, or the solver possibly has reported some cell metrics that it's not happy with in some portion of the grid. And that's pretty common and usually comes back as coordinates from the solver. Well, the next thing you need to do is to be able to visualize or find where that is in Pointwise if you're coming back to Pointwise to look at your mesh and do some diagnostics. One of the ways that I like to do that and suggest to users to visualize a location for points that have been reported is to just simply use the center of rotation. We actually have a panel in the code, a command panel in the view menu that allows you to set the rotation point explicitly. So if I click on Set Rotation Point, it opens a very small, simple panel where I can go in and type in some coordinates. And this is just some example coordinates from some cells that I was looking at previously in this particular grid. So I type in X, Y, and Z, I hit Enter, and I can see that the center of rotation axes, the red representation of the center of rotation, has moved. So I click on OK. That's going to stay there now until some point when I decide to move the center of rotation again. I can go up here to the View menu again and click on View Show Domains to turn them off. And then I can rotate the model around. And of course, this is my new center of rotation. And I know now that that's the location of the area that was reported perhaps by my flow solver. And so then I can use other diagnostics like the examine command to go through and look at my grid in that particular region. So for instance, I might select this block and go to examine minimum included angle. For example, go to the Cuts tab, enable cutting, and this is a Cartesian cut. We probably really want to look at a IJK plane, and let's just do a K, and I can cycle this into the area where my center of rotation is so that I can see the cells in that location. So that's just a little trick that you can use to try and locate or find points in the interior of your volume when you may not have a good feel for where they are visually. The other thing that I would like to just talk about briefly is being able to locate min values and max values for a particular diagnostic. So this particular set of blocks, let's go and change our diagnostic to Jacobian. This gives us a Jacobian analysis of the entire block, and I can see immediately that I have some cells that are being drawn here in the display window. And that's one of the nice things about the Jacobian analysis, is that not only do I get a table summary of cells with problems, but I also have those individual cells rendered automatically according to these checkboxes. So I can turn them off and on, but by default they're on and I can see them. There could be some situations, though, where these cells are so small that they're even hard to visualize even when they're being rendered. And one way to get around that is to go to the Extrema tab and to tell PointWise to zoom to the minimum value of this particular diagnostic. When you click on this button, it also turns on the rendering of that cell with this checkbox automatically. It zooms to extents on that particular cell, and you can easily see where it's located inside the interior of the grid. In addition, this particular cell has its boundaries represented, or its corners or vertices represented by nodes. Let's go back to the Examine tab and turn off these other cells so that we're only seeing the min cell. You see, again, as I mentioned, we have nodes here on the corners of this individual minimum cell. That means I can select those and move the rotation point to that location, which is very handy. So then I can rotate my model now about that cell, and it gives me an easier way to see what's going on with the grid. And of course I can easily see that I have a connector here that folds on itself and is the likely cause of this particular problem. One last thing that I'd like to demonstrate before we wrap up is I'm going to go back actually and turn off this minimum cell. On the Examine tab, I'm going to turn on the negative and negative skews and show you one other trick to finding cells that are being rendered, and that is the shrink factor. Sometimes, again, these cells may be so small, and they may be distributed throughout the grid. They may not all be located about the minimum valued cell. There could be other cells at the opposite corner of this block that also have Jacobian issues. We can set the shrink factor to a value of 0, and that tells PointWise to render all of those cells as a node about their centroid. Nodes are always rendered at the same size in the display window regardless of zoom level, which makes them easy to see and point out. If we turn off our cut plane, and if we had a really dense grid with a lot of connectors and a lot of connector nodes being displayed, we can also go to View and Show Nodes, so that now all we are seeing are the nodes of the cells that I'm displaying. So that's another trick for visualizing problem cells in your grid. Okay, that's all I have for my demos for today. I would like to open up the webinar now to any questions that you may have. So please open up your questions panel in your webinar window and use that to type in any questions that you have.